In this lecture, we're going to learn how to solve a large class of first-order differential equations called separable differential equations. And the method is called separation of variables. So suppose we have a differential equation. Suppose we have a first-order differential equation. Recall that first order means that the highest derivative that appears in the differential equation is a first derivative. So we don't have any second derivatives, third derivatives, or higher derivatives. So suppose we have a first order differential equation of the form dy dt equals some function of y and t. So this notation, I'm just saying this side is some, perhaps very complicated function involving the variables y and t. And we can isolate the derivative dy dt on this side. Okay. So a differential equation of this form we're going to call it separable if, so it's called separable if we can write it in a slightly different form. So we want to be able to write it in the form some function of y alone without t times dy dt equals, and then on this side we should just have a function of t, so g of t. Okay. So if we can write a differential equation in this form, we call it separable. Let's look at some examples. So examples. For the first example, let's do y prime equals y squared plus t cubed. So is that separable? Well, if we move this y squared over to this side by subtracting it, then we have a function of y plus y prime equals some function of t. But notice that we really need multiplication here. Right, so we need some function of y alone times the derivative of dy dt. And it turns out there's just no way to do that without also moving this t over on this side. So this one we can actually, it turns out we cannot write it in this form. So this one is not separable. Let's look at another example. So what about y prime equals e to the x plus y. Okay, so this time x is my independent variable, y is my dependent variable. Note that the meaning of y prime should always be apparent from the context, right? Because we're only working with differential equations here with two variables. So here, this is dy dx, and this x is our independent variable. So is this separable or not separable? Well, at first it might not look so separable, but notice that, let's go over here, we can use a property of exponents to write this side as e to the x times e to the y, and then we can divide by e to the y, or multiply by e to the negative y. We have e to the negative y times y prime equals e to the x. And that's exactly in this form, right? So we have just a function of y times the derivative equals just a function of x on this side. So this one is separable. Okay. And I just want to share an obvious but important fact. So here's a fact that we're going to use a lot. any differential equation of the form dy dt equals just some function of y alone. So we don't have the variable t appearing in a differential equation at all. That is going to be separable. And you can probably see why. No matter what this function is, even if it's extremely complicated, we can just divide both sides of the equation by it, and then we get 1 over that function over here times dy dt equals, I guess, just the number 1 we're going to be left with here. So that's certainly of this form. And this is actually important because I think pretty much all of the differential equations we saw in the first 2 lectures are of this form. They didn't have the variable t appearing in a differential equation. Okay, so actually let me give you a quick problem to try. So here's a problem. Is the differential equation, here I'll give you the differential equation, so it's going to be y prime equals xy plus x plus y plus 1. Is this differential equation separable? Okay. And before you just say no right away, make sure you give it some thought. Maybe there's a way to rewrite this this right-hand side. So think about this one for a bit. You can pause the video if you want. And so we'll go ahead and continue. Okay, so we know what separable means. Let's actually talk about how we will now solve separable equations. So solving separable equations. Okay. And I really think the best way to learn how to do this is to just start doing an example. So let's look at a first example. It's better to see this concretely in the form of an example. So we'll actually take one of the differential equations from the first lecture, dy dt equals negative k times y. And we're trying to solve for, so the goal is to find a function y of t. Okay, that's our goal. This was actually the radioactive decay example from the first lecture, where y represented the number of carbon-14 atoms. Although this differential equation actually comes up a lot, and in a lot of other examples also. So the first step is going to be to, so this is step 1, it's going to be to separate variables. What do I mean by separate variables? I mean, write it in this form. Right, so we have just a function of y on this side times the derivative, and then just a function of t on the other side. Well, if you notice in this one, there's actually no t at all on this side. So, but we do have to move this y over. So we'll get 1 over y times dy dt equals negative k. If we want, we could have divided by this negative k also, or we could leave it on the right side. I mean, this certainly is a function of t. Doesn't have t in it at all, but that's okay. It's just a constant. Okay, so that's step 1. I just want to notice one thing. So that this step is only valid if y is not equal to 0. So if y equals 0, we need to maybe use some different logic. But for now, let's not worry about that. So for now, if we can divide by this y on both sides to write it in this form. And next, what we're going to do, okay, before I write the next step, I actually just want to notice something here, which is we have a function of y here, and then we're multiplying it by dy dt, by the derivative of y with respect to t. Doesn't this look like the answer to a chain rule derivative problem? So if we have a function of y and we take its derivative with respect to t, we're always going to end up multiplying by this dy dt at the end, by the chain rule. So this is, I just want to make a note of this. This thing right here is actually just, this is the derivative of natural log of y. Right? This is the derivative of the natural log of y with respect to t. With respect to the variable t. And so that actually suggests what we should do next. So let's take advantage of this fact, and we're going to integrate both sides. Integrate both sides with respect to t. So this is what it's going to look like. We have 1 over y times dy dt. dt, we're going to integrate. And on this side, we have negative k dt. We're also going to integrate with respect to t. And what do we get? Well, on this side, we just get, like we said, we noticed that this was the derivative of the natural log of y. So this is just going to be the natural log of y. And on this side, what do we get? We get negative k t. And there are two things that I forgot here. So the first, we need arbitrary constants. Technically, we need one on both sides, but if we had one over here, we could just subtract it over to this side. So we actually only need it on one side. So I'll pick the right side. And the other thing is, and this doesn't matter if this function y only takes positive values, but if it takes negative values, the domain of this function here, 1 over y, is actually all real numbers except for 0. Whereas this function here has a smaller domain. This only y can only be positive real numbers here. So if we want an antiderivative that has the same domain as 1 over y, we need to put absolute value bars on this y. So yeah, this is an antiderivative of 1 over y that has the same domain. And before I go to the next step, I just want to show you a quick shortcut. So how should I do this? Maybe over here. So starting from here, here's a shortcut. So actually what you can do here is multiply, so treat this dy dt as a fraction and multiply by dt. Okay. I mean, this should look a little bit weird, right? Because dy dt is not actually a fraction, right? It's a symbol that means the derivative of y with respect to t. It's not a fraction. But in a lot of applications, we can actually treat it like a fraction. And if we do that, then just draw integral signs on. This dy and this dt is actually telling us, so this side is telling us integrate with respect to y. The integral of this with respect to y is, again, yeah, just this right here, natural log of y. So this integral and that integral, we both get natural log of y. This integral right here is negative kt plus c. So this is a good trick to keep in mind. You can treat this dy dt as a fraction in this step when you're doing the integrals. Okay, am I forgetting anything? I think that's it. Yeah, definitely this constant c is very important because that's actually going to be where our infinitely many solutions to the differential equation come from. Okay, so the final step is just going to be to solve for y. So solve for y. And I think we have just enough space to do that. So if we exponentiate both sides, we get the absolute value of y is e to the negative kt plus c, all up here in the exponent. And if we'd like, we can rewrite this using our properties of exponents. So e to the negative kt times e to the c. And here's a question for you. So how do we get rid of the absolute value bars in an equation? Let's stay on the same piece of paper, so we'll go over here. So what we do is, we can get rid of them, but we have to add a plus or minus to the other side. Plus or minus e to the, so I'll write the e to the c first. That's just a constant, right? And then times e to the negative kt. Right? And the reason for this is, y could either be positive or negative, right? And the absolute value bars are always making it positive. So if we get rid of the absolute value bars, we introduce this ambiguity of the plus or minus. And I'm just going to clean this up a little bit. So actually y is going to be equal to plus or minus e to the c. Whatever that is, it's just a constant. So that I'm just going to replace with another constant. I'll call it capital A. So that's what's typical. Times e to the negative kt. And we're done. So this is actually our what we're going to call the general solution to the differential equation. This is the general solution. It's called the general solution because it includes all possible solutions to the differential equation. So each solution is actually going to correspond to a choice of this parameter a. And in this case, this actually worked out really well because remember up here, this step right here is not going to be valid if y equals 0. So we might say, well, wait a second, maybe we shouldn't let a be 0. We could let a be anything else except for 0. But we can actually also let it be 0 because we get y equals 0 if that's the case. And you'll notice that actually 0 is a perfectly good solution to this differential equation, right? You can check. Just the function y equals 0. If you can plug it in on this side, you get 0. And then the derivative of 0 is 0. So we get 0 equals 0. That's a true statement. So really, a here can be any real number, including 0. Positive, negative, or 0. And this is our general solution. So we just solved our first differential equation from scratch using this method of separation of variables. So I'd like to do another one. So this one, maybe we'll introduce a new idea. So this one will be an example of a, so this will be an initial value problem. Initial value problem. And okay, so let's consider the differential equation y prime minus y squared equals 1. I think I took this one from the first lecture again. Okay, so here's our differential equation. And what I want to do is I want to find a solution, y of t, such that y of 0 is actually going to equal 1. So I want to specify the initial value of the solution. So that's an initial value problem. An initial value problem is a combination of a differential equation and an initial condition. All right, so here we have the differential equation. And a statement like y of 0 equals 1 is called an initial condition. And the solution to an initial value problem, well, that's just going to be the function y of t that satisfies, well, of course, it's going to satisfy the differential equation, but it also is going to need to satisfy this initial condition. So its value at 0 has to be 1. So let's try it. So it's There's basically just one new part at the end that we're going to add. But let's start by solving this differential equation. Is this a separable differential equation? Well, it's not written in the correct form right now for a separable differential equation, right? Because we need multiplication over here. We have subtraction. That's no good. So the first thing we need to do is actually just move this y squared over to the other side. And maybe I'll rewrite this as dy d. Actually, I don't know what the. I guess we have t here. Yeah, so dy dt. And yeah, I mean, this has to be separable, right? Because this is just a function of y alone. It doesn't involve t. And so the way to do it is just to divide by this entire thing here. This looks really strange the first couple times you do it. Dividing by the entire right side and just leaving a number 1 here. But this is going to be a typical idea. So we have separated variables. That was step number 1. What are we going to do next? Let's use that trick where we actually also split up the dy dt. So we have dy on this side, and then we have 1 dt. And then we just integrate both sides. This side with respect to y, this side with respect to t. And some of you might recall this integral. This is actually a just sort of a known integral. It's actually hard to do this integral, but this is the arctangent integral. Arctan y. That's a good one to just have committed to memory, actually. The integral of 1 over 1 plus y squared is the arctangent of y. That one comes up a lot. So we need an arbitrary constant, but I'll put it on the right side. So here we have t plus c. And let's solve for y. So we get y equals, well, how do you undo arctan? You take the tangent of both sides. So we get tangent of t plus c. Great. So this is our general solution. This is our general solution. I just want you to notice how actually the c, the arbitrary constant here, actually ends up inside the tangent function, right? So definitely you can't just wait until the end of this whole process and then tack on a plus c. You have to. The plus c comes into the picture exactly at this moment, right? When you do the integrals. So here it actually, yeah, ends up inside here. So we're sort of horizontally shifting the tangent function. Oh, but we're not done yet, right? So we actually just want the specific solution that passes through 0, 1, right? The point 0, 1. Well, how do we do that? That's not difficult. So we're just going to use this fact. So use the fact that y of 0 equals 1, and then we'll just plug in these numbers and see what the c has to be. So what happens when we do that? We get 1 equals the tangent of 0 plus c. Right? So 1 equals the tangent of c, which means that c has to equal, well, what angle has a tangent of 1? Pi over 4 is one example. Actually, infinitely many examples, right? But pi over 4 is certainly one possibility. So this is a solution. Y of t equals tangent of t plus pi over 4. And if we choose another angle here that works, right, we could, for example, we could add pi to the solution and get 5 pi over 4. If we chose 5 pi over 4, we'd actually just get the same function because the tangent function is periodic with period pi. Great. So this is actually our solution to the initial value problem. The solution to the initial value problem. I'm actually going to write IVP for initial value problem, just because it comes up so much. So when you see IVP, that means initial value problem. Okay, so hopefully you've basically got the idea of separating variables. I do want to do another one though to show, maybe one more sort of tricky idea that could come up sometimes. Here's another example. So this time we'll do another initial value problem. So we'll find an explicit solution to the initial value problem, the IVP. And we'll have, this time let's use x as the independent one, just to change things up a little bit. Dy dx equals x over y. And it's an initial value problem, so I have to give you an initial condition. So we'll say y of 1 equals -2. And what do I mean by an explicit solution? Well, I just mean a solution like this. That's a function that's solved for y, essentially. Right? So we have y equals then just some function of x. That's an explicit solution. Okay, so this time, we do have the variable x appearing, but that's okay. So we want all of the x's to be on this side and all the y's to be on this side. So we just multiply by y. So we have y times dy, and then we'll multiply by dx. So we have x times dx on this side. We'll take the integral of both sides. And so this will be 1/2 y squared equals 1/2 x squared plus c. We might as well multiply by 2 to get rid of those 1/2s. So we get y squared equals x squared plus, technically I should write 2c, but I'm just going to write c again. So we're going to replace what would have been 2c by just c again. This is something you can do also. So 2c is again just an arbitrary constant. So we're essentially just renaming the constant. Kind of like in that first example where we replaced e to the c by capital A. Okay, so we're done. Yeah, we just have one more step here. So let's solve for y. We get y equals square root of x squared plus c. But I forgot something here. Can you see what I have to add? So this is actually a really typical mistake. So I'll put a warning over here. When we took the square root of this left-hand side, so the square root of y squared is actually not equal to y. And that's because when we square a number, it's always going to be positive or non-negative, right? And when we take a square root, this symbol means you take the positive square root. And so we're always going to get a positive number. So the square root of y squared is actually equal to the absolute value of y, because this y could have originally been negative. And so we actually have an absolute value of y over here. But remember how we deal with absolute values. You can get rid of the absolute value, but then we have to introduce a plus minus sign. So y is actually either plus or minus square root of x squared plus c. C is our arbitrary constant. And again, let's use our initial condition. So we're going to use the fact that y of 1 equals -2 in this case. And so we plug in -2 for y, and then we have this plus or minus, this unresolved plus or minus. I'm not sure what to make of that yet. And then we're plugging in 1 for x, 1 squared is 1, and plus c. So we're trying to figure out what c is, right? Because the c is actually what's giving us our infinitely many solutions. We want to sort of pin that down to one value. Okay, well, we have a square root with either a plus or minus equaling -2. So this thing inside the square root has to be 4, right? So it tells us that c equals 3. But there's something else going on here. In order to get this -2, we actually had to choose the minus, right? So we have to choose the minus. for our particular solution here. Because otherwise, we can't satisfy this initial condition, right? So we have two elements of choice here. We're choosing a value for c, and we either have to choose the plus or the minus. So when we write down our solution, it's going to look like this. It's going to be y of, I guess, x in this case, is going to equal, so c is 3, so we have square root of, minus should not be inside. It's not working. There we go. Square root of x squared plus 3. And then we need a minus sign outside, right? So we want an explicit solution. We don't want any ambiguity still having the plus or minus, right? We need to choose the minus sign in order to satisfy this initial condition. So this is our solution to the initial value problem. And so that is the method of separating variables. We're going to see that actually a lot of differential equations that come up in real life are separable. So for the next, I think for the next 2 lectures, we're just going to be going through examples and doing some problem solving with separable differential equations.